All right, so good evening, each one of you present here. I'm the Vice President of Microsoft Innovations Club, and I would like to thank and welcome each one of you to the day two of our competitive programming knowledge sharing session. I would like to thank our respected faculty coordinator, Anusha ma'am, for letting us host this event and supporting us throughout. Today's speaker is Sanjay Saju Jacob, an experienced competitive programmer with a rank of 1401 on Code Forces. He's here to share his knowledge about time complexities and in depth, he'll be covering all the concepts. So let us begin. Over to you, Sanjay.
Hi guys, I'm Sanjay and today I'll be taking the session and we'll be covering a few concepts today like time complexity, space complexity, and also in the end I would like to talk about um, competitive programming as a hobby. So is my screen visible right now?
Yes, Sanjay, you can go ahead.
Okay. So the first concept we learn about, I guess, in these 4 weeks is the most basic one, which is time complexity and space complexity. So time complexity there's a definition right here, is the amount of time taken by an algorithm to run. And this depends on the number of elementary operations that must be performed. And this in turn is also dependent on the size of the input for the given problem. So it measures the time taken to execute the statements in an algorithm. So this is a basic, just a basic definition of time complexity. And the same way, just as time complexity is there, space complexity is also there for memory. It talks about the total space taken by the algorithm with respect to the input size given to that algorithm. So space complexity not only depends on the input size, but also depends on auxiliary memory that may be used, to perform different processes on the input. So yeah, so these are just definitions. I'm just starting the definitions. And the first notation that we'll see in time and space complexity is the big O notation. The big O notation talks about the largest or the asymptotic, the upper bound of the time complexity of an algorithm. So like how much time an algorithm will take to execute, and that maximum time is what the big O notation defines. And the same big O notation is used to talk about the upper maximum bound of space complexity also. So yeah, let's just have a look on what is time complexity, what is space complexity. I'm just going to give a very basic idea to you with just an example. So let's just assume, okay, that we have a number n and we have a number x, and we are given an array of n numbers, a1, a2, a3, so on till an. Okay, so we have an array of n numbers, a1, a1, a2, a3, so on till an, and we are also given another number x, and we are asked to find, let's say that we are asked to find the value of x in this array. Okay, so we just have to compare the values in this array with x and find if x exists in this array. So let's just say, okay, let's just see what all are we doing here. So what we'll be doing here is we are going to compare. First, we'll compare x with a1, we'll compare x with a2, okay, and we'll compare x with a3 and so on. Okay, so the elementary operation, like you all saw in time complexity, when we defined time complexity, it talked about the number of elementary operations that must be performed. So an elementary operation in this case is just this comparison process where we compare one element of this array with one of these elements of this array with x. That is the most elementary operation in this case. And now, if we want to find the time complexity of this process in terms of big O, I'll show it to you now how we can see the time complexity of this. So what do we have to do here? So like we said, we have to find we have to see if the value of x exists in this array. So let's just assume that X value does not exist. Okay, it's not there in this array at all. So when we are searching, we'll first compare with X with A1. Okay, we'll understand it's not X is not equal to A1. We'll compare X with A2, with A3, and so on. We compare X till we get AN, till we compare it with AN. And so here, right here, we perform this elementary operation of comparison. We performed it n times. Okay, so we perform this n times, and hence this complexity is described in terms of big O notation as order of n. That is, we did this elementary operation n times, and this is known as this is called being order n. This is an order n operation. Okay, so the so this is the thing right here. And we also saw in the definition of big O, the big O order, big O notation, that it is the maximum. It talks about the maximum amount of time. That is the asymptotic upper bound of an algorithm. Okay, so I'll show you how it talks about the maximum amount of time. Just imagine if X was existing in this array. Okay, let's say X was A1. If X was A1, when we compare X and A1, we already, we can end the algorithm in this step. Our idea was to try and find if X is there in this array, and if X is equivalent to A1, we finish in one step. We finish the full algorithm in one step. If X is equal to A5, we will compare with A1, A2, A3, A4, A5, and we'll finish that in 5 steps. And in the worst case, if X is not there in the array at all, we'll compare with every single element, and that will be n steps. Right, that is the maximum case. So that's what order n means. This means that in the worst possible case, it will take n steps, that this elementary step will have to be performed n times. Right. So that is what order n says. That is the worst case worst case time complexity that can occur. So similar to this, let's just see, just to get a better understanding of time complexity. Let's just see another example. Okay, we are going to see the same example of searching itself, but this time with a matrix. I'll show you. So basically, let's say we have same as before. We have a number n, and we have another number x. Okay, and this time we are given, instead of an array. Okay, let's not call it A then. Instead of an array, we're given a matrix. Okay, we're given a matrix, and it has these elements. It has what A11, A12, A13, so on till A1n, A21, A31, so on till AN1 and ANN. Right, so like this, imagine this is a matrix that is given to us, which is of size n into n. Okay, so it's an n square matrix, like there's n rows and n columns. And this time again, they have asked us to compare and is to find the value of x in this matrix. Like if it is there, we have to search. We would search if the value of x is there in this matrix. So again, let's think of the worst case that can occur. The worst case that can occur is that this value of x does not exist in this matrix at all. So then how will we start searching? So we'll start searching, we'll search, we'll check, compare x and A11, we'll compare x and A12, so on, we'll compare till x and A1n, and then we'll go to the next row and check A21, compare with A22, and so on. So like this, we will compare with n into n elements. You understand? In the maximum worst case, we'll have to compare with n into n elements. That is, we'll have to perform this elementary operation of comparison with n into n elements. And this becomes order of n square. N into n is n square. So this is what we call order of n square. That is, in the worst case, the time complexity is order of n square. So you understand. So now this in this way, we looked at two examples of time complexity. Say space complexity is no different. It's same thing with memory. So let's just look at in terms of this example itself. Let's just look at it. So let's just say again, as in the first case, we have a given n, okay, and we have a sequence of numbers A1, A2, A3, so on till AN. Now, again, as in the first problem, we have a number n, we have a sequence of n numbers, and we have an x. So let's just say that again, we have to compare the value of x with these numbers and find if x and say if x exists in the sequence of numbers. So now let's talk about the space complexity of this problem. Let's just say that I store these values in an array. Okay, I store all these values or the sequence of values. I store it in an array. Okay, let's just think like that. So a1, a2, so until an. I store it in this array. Okay, imagine that. So now look what happened. One, this right here is a unit of space. Okay, when we stored this all n elements in array, this is 1 unit of space. We used such n units of space. Okay, so we ended up using n units of space. Okay, so since we use n units of space, this is known as order n space complexity. Okay, so this is 1 unit of space and we used n of those units. And as n becomes bigger, the size of this array also becomes bigger and that much more units of space we need to use. So it's dependent on n, and that is what we call order of n space complexity. Okay, so now let's just say this is order of n space complexity. Let's just say we approach this problem a little bit differently. Alternatively, let's see how we can reduce the space complexity of this problem. Okay, let's say I kept a temporary variable k. Okay, and I say initially I say let k, I get the value of a1 and I put it in k. I get the value of a1 and put it in k. Then I compare k and x. Okay, and then I erase the value of a1 from k and put the value of k2 of a2. Sorry, I erase the value of a1 from k and put the value of a2. Then I compare k and x again. Then I erase the value of a2 from k and put a3, and so on and so forth. I can do this operation till k is equal to an. Okay. This time, look at how I was able to reduce the space complexity. See, last time we allotted n units of space. Okay, but this time we only needed one single variable k, right? So, and this one single variable k only uses 1 unit of memory. So right here we only need to use 1 unit of memory, and hence this would be order of 1. This is, we used constant space. Okay, so um, that's how we can reduce the space complexity. So now you have through 2 examples, you have a pretty good idea of what space complexity is and time complexity is. Now, just before we stop talking, like if we move to the next topic, I just want to say one misconception that people might have about, just to remove a misconception about space complexity and type complexity, is this, that let's say there is an algorithm, okay, which performs something with in 4n. It takes 4n steps to complete that algorithm, and n is the number of inputs. Like a similar algorithm like we did right now, it took 4n steps. We still call this thing's time complexity as order of n itself. We don't say order of 4n, because right here the rate, like the what do you call time complexity determining factor right here is n. So we only acknowledge that factor, only the most important factor only do we acknowledge when we write in terms of complexity, because this makes all the difference. If n goes from 5, if n is 5, this is a very small time complexity. So if n is 10 raised to 8, this is a very large time complexity. So it depends on n. Hence, we only acknowledge n while writing it in this notation. Similarly, for example, if it is like, let's say there's an algorithm that completes the process in 12n square, completes the process with time complexity 12n square, then again, like we say it's an order of n square algorithm. That is the time complexity of the algorithm is order of n square, because this is the only, um, determining factor. Like this 12 is constant, it doesn't change. So this right here is the only, the size of n square only do we need to take into account. So similarly, also for constant number of steps. So let's say there's an algorithm that we're doing which does not depend at all on the input, on the number of inputs. Let's just say it depends, like it takes 4 steps no matter what. It takes only, I mean, not 4 steps. Yeah, it has a complex, like it takes 4 steps only to complete no matter what. Like if that is the case, even then we call it order one. You understand? It doesn't need to be only one step alone. If the number of steps taken is constant, then we call it order one. This signifies constant time. Constant time. This right here is not constant, right? Because it depends on n. This also depends on n. As n increases and decreases, the complexity changes. But here, no matter what, only 4 steps it takes. So it's called order one constant. I'm saying if it's like just 7 steps, even then we call it order one because there's no change in the number of steps depending upon how much input is coming. So this is constant time. So I just wanted to remove this misconception that people may have. And same applies for space complexity also. Similarly, one more thing I'd like to just say about space and time complexities. Let's just say there is a algorithm out there, something it does something, and that algorithm's time complexity is defined by function 4n square plus 8n. Oh, wait, sorry. 4n square plus 8n plus 6. Okay, let's just say the time complexity of that algorithm, it is defined by this particular polynomial. So how would we write it in the big O notation? How would we say complexity is? We would still only acknowledge n square. Okay, we say if this is the complexity, if this is the amount of time taken by the if the amount of time taken by the algorithm to execute is defined by this function, we say that the time complexity is order of n square. The reason being that here also see, if you see, the real time complexity determining variable is only this n square, because see, if n is equal to 5 or 6, which is very small, all these terms are relevant. But just imagine if n is equal to like 10 raised to 6, okay, or let's take a small value, let's take it as 10 raised to 3. If n is 10 raised to 3, this is 4 into 10 raised to 6 plus 8 into 10 raised to 3 plus 6. So this is 4 million, or yeah. And this right here is negligible, right? This is very negligibly small number of steps. If you add 8,006 into 4 million, it does not make a difference. So this right here, this n square term is only acknowledged when we are saying in terms of um, the big O notation. So yeah, so this is all the information that I had to give about time and space complexity. Now what we'll do, okay, yeah, so before we go, we understood the big O notation. Just here's a graph that shows how the big O notation grows with size of n. So on the x-axis right here is n, and on the y-axis is like the order of n, the time complexity. So see, order of 1 is constant. It means there's a fixed amount of time in which the algorithm executes, and it's irrespective of the number of inputs. So that's constant. Log n is grows very gradually. N grows linearly. N log n grows with a little bit more slope. N square grows really fast. N cube faster, and 2 raised to x is really fast. And factorial obviously is bigger than all of these. It grows extremely fast. Like when n becomes like 10 itself, it goes extremely high. So yeah. So this is just a graph showing for information is to give you a better idea of how complexities work. Now, okay, before I come to this right here, there are also 2 more notations that are used, which is omega notation and theta notation. Okay, so it's just like like okay, I guess I don't need to even write down omega notation, theta. Just like here we use big O notation, omega and theta notations are also used. The omega note, like we saw that the big O notation is used to show the maximum complexity that can occur, right? Similarly, omega notation is used to show the minimum, like the lower bound that can occur, like the minimum complexity, the minimum number of steps that can be taken by the algorithm. It's shown by this um, by the uh, omega notation, and the theta notation gives a bound, like it creates a bound between the upper and the lower it creates an upper and lower bound for our complexity, and it gives an idea of the average case. Now, like for competitive programming, you don't really need to give too much attention to these two notations because they are not very relevant. Like you can, I would say that we'll never probably use them in a problem ultimately, because in the end, we only care about the maximum, this maximum complex time complexity it can go to, because if you reduce the maximum, then you don't need to worry about the rest, right? So you all can just focus on big O notation itself. If you want, you can read a little bit on these, but like it's fine. Yeah, so that's all. I just gave a basic definition of what they are. Um, so now let's just go on to a real algorithm, just a simple algorithm to start off this idea of time complexity and space complexity, and how you can actually predict, like roughly determine something's time complexity. So I have I have another slideshow to show. So this is the sieve of Eratosthenes algorithm. So basically, what this algorithm does is very simple. It is to determine the number of prime numbers um, till a given value. So if you're giving me a value n and you're telling me find all the prime numbers less than n, all of them, it will find it for me in this time complexity and in this space complexity. So this is very smart. So I'll show you. I'll tell you what I mean. In the traditional, way, if you want to traditionally, if I'm okay, this is the problem. So this is the problem that is given to me. I have a number n, and the problem given to me is I have to find all prime numbers p. Let's say p is a prime number, okay, and I have to find all prime numbers less than n. Okay, so less than or equal to n. If this problem is given to me traditionally, like normally, how would we do it? We would first go from iterate from 1 to so on till n. We'll first check each. Let's say we have a number k in between, like we have a number k in between. We'll take k and we'll check if it's prime by iterating through all the factors of k from the beginning, 1, 2, 3, 4, by trying to find all the factors of k. If it has only two factors, then we'll say this is prime, and um, you understand, then we can say this value k is prime, which is less than n. But just imagine how long this process is. This thing's complexity is like very, very high, because first of all, you have to iterate through all values till n, and for each value, you have to find all the divisors by iterating through all values up to it. So 1 to k, you iterate through, and you have to search if each of these are divisors of k, and then you have to, if there are only two divisors, then k is prime, and then you mark k as prime here. You go to k plus 1, and then you do the same thing. You go to k plus 2, you do the same thing, so on till n. So this is a very tedious process, to manually check if it is prime. So C of Erasmus is a very nice and simple algorithm that gives you a way to do this with very less complexity. So this is the time complexity. This is very less actually. Okay. And I'll show you what the algorithm is. Uh, Basically, this is the algorithm. So yeah. So in C of Erasmus, let's just take this example. Let's just say that we want all the prime numbers beneath 149. Okay. So this is the number over here. The end number is 149. And we have created an array like this. Okay. So we need all the prime numbers before 149. So what the C of Erasmus algorithm says is that it says if I go, let me like what the C of Erasmus algorithm says is that it will iterate to every element, okay, less than this 149, and see how many multiples of that element is there ahead of it. So I'll tell you what this means. So basically, so initially we'll zero and 1 we do not consider, because 0 into anything is 0 itself, so it is marked as not being prime, and 1 is a special case, a unique number, so it's not prime or um, composite, right? So we'll start from 2. So what C of Erasmus says that 2 is right here, okay, and we reach 2 let's mark all the factors of 2 as not all the factors, all the multiples of 2 as being non-prime. So let's just mark 4, 6, 8, 10, 12, 14, 16, so on, 148 and so on as non-prime. You understand? So like this. So when we reach 2, we mark all its multiples as non-prime. Okay. Now let's go to next value, 3. So 3 is an unmarked value. So this gray is marked values, marked as being non-prime. Okay, so 3 is unmarked, so we know it's prime. Currently, we know that it's prime because it's unmarked. And then again, see of Erasmus algorithm says, let's just mark all the multiples of 3 as not being prime. Okay, as let's just mark all the multiples of 3. So 3's multiple 6 is already marked. 9 will be marked. 12 will be marked. 15 will be marked. 18 will be marked. 18 is already marked. 21 will be marked. Like that, it will go forward and mark all the multiples of 3 as not being prime. Okay, so there we sorry, once again. So we marked all the multiples of 3 also as not being prime. Now we reach the next value 4. So 4 is already not prime, so we can skip that. It's already been marked as not being prime. You can skip that. 5. 5 has not been marked yet, so that means 5 is prime. So till reaching here, as of now, 5 has not been marked, so we can see that 5 is prime. So now again, the algorithm tells us mark all multiples of 5 as prime. So 5's next multiple, all multiples of 5 which are not itself, obviously. So next 10, 15, 20, 25, 30, 35, so on, all will be marked as not being prime. Okay, so like this and so on. We do the same process for, we go to 6. 6 is already marked as not being prime. We do the same process for 7. Okay, now 7 is prime because like we, as of now, it has not been marked as prime, so it has not been marked as not being prime, so it is prime. So we go ahead and mark all the multiples of 7 as being prime and so on. And finally, we can, if we continue this algorithm throughout till 149, we get all the unmarked values as prime. See, so ignore 1, 0 and 1 are special cases. 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, all of them which are prime have been marked as being prime, which have been left unmarked, sorry, and all that are not prime have been marked as in gray color. Okay, so this is the algorithm of C of Erasmus, and I'll just give you a better idea. I just copy pasted a code that I created. So this is the case. So initially, we just create an array. Don't worry about the syntax and all if you don't know. This is just an array that is being initialized. So the elements of this array, okay, the indices of this array represent the numbers, and the element of this array tells us whether it's a prime or not. So if the element of this array A, if for example, if A of 5 is not prime, right? A of 5 is not prime, so it will have a 0. It will be marked as 0. If A of prime, A of 6 is, it is not prime, so it will be marked with a 1. So like that, we are just creating an array, and here is the a for loop. So see, first we start from 2. Okay, 2 is all values have been initially marked as not being prime, as being prime. 0 and 1 are exceptions because they are unique numbers. Now we start from 2, right, and we go forward and we mark all multiples of 2. See, so right here we mark all multiples of 2 as being non-prime, and similarly in the next iteration I will become 3. We mark all of them as being non-prime, and so on and so forth. And finally, we can, all the values that still have 0 are considered to be prime. So just if you want to see this algorithm in action, I can just show it to you. There's the same algorithm. So let's say 18. Okay, so you can just run this. And there you have it gives us all the prime numbers 2, 3, 5, 7, 11, 13, 17 that is less than all d prime numbers less than 18. Now, so this algorithm has a bizarre complexity, right? So we saw the complexity that that was shown to us, which was this. This is the complexity. Now let's just say it's difficult to derive this complexity, but let's see how we can, derive how we can get an idea of deriving a complexity for this or approximating the complexity of this particular algorithm. So this is the thing. So for in this algorithm, if you just look at it, each time we reach a composite number, okay, we just skip over that composite number. Okay, so each time, so we reach a composite number and we skip over it, and each time we reach a prime number, we also visit all its factors, its factors, like not factors, sorry, it's all its multiples. So what happens is, let's see. So if let's say we were in 2, when we reach 2, we will be visiting n by 2 elements. Like, so when we reach 2, when the pointer reaches 2, we will visit 4, 6, 8, 10, 12, so on and so forth. We visit n by 2 elements. When it reaches 3, we visit 6, 9, 11, 12, 15, so on. We visit n by 3 elements. Okay. When it reaches 5, when it reaches 4, we do not visit any elements because 4 is not prime. When it reaches 5, again we visit n by 5 and n by so on, n by 7 we visit, when reach 7 we visit n by 7 and so on, like this. Okay, till n by p, where p is the largest prime less than largest prime largest prime that is less than n. Okay, p is the largest prime that's less than n. So you see how it works. And as for the and this is the number of steps for when we reach a prime number, and when we are not reaching a prime number, we just skip it. So there, when we are not reaching, we are reaching a composite number, we just go to the next step. So that would be, let's say there are total of, k primes inside this. Okay, there are k primes less than n. The number of primes that is less than n is k. Okay, so then we will be visiting n minus k nodes, n minus k numbers, and skipping over them. So if we visit 4, let's say we visit 4, if we visit 4, we don't do any other process. Like if we visit 4, it does this for loop iterates the next element. It does not go into the inner for loop. Similarly, if we visit 6, 8, 9, so that in total, that is all the composite numbers, is n minus k steps. Okay, so n minus k. I think somebody's unmuted. Okay, so that would be all the other composite numbers together is n minus k steps, and the prime numbers form these many steps. So now you'll say, how do we derive the time complexity from this? Like, this is a very weird.
What's k once? Can you repeat it once again?
Okay, yeah. K is basically just the number of primes. Okay, just the number of primes less than n. So what I'm trying to do with k is basically what I'm saying is, if it reaches a prime number, let's say some m is a prime number. Okay, if it reaches a prime number m, then sorry, if it reaches a prime number m, then we enter this for loop. Okay, this internal for loop, and we perform n by m operations inside this for loop. Okay, we visit n by m elements inside this for loop. But if it is not a prime, we just visit, we only we skip over to the next one. So if it is not a prime, it's 4, we just move to 5. You understand? So there only one step is involved. If it is a prime, we have n by m steps because it goes into the inner for loop. So all I'm trying to say is that the composite numbers together form these many steps, where k is a total number of prime numbers. That's all. K is the total number of prime numbers, and so the total number of composite numbers is n minus k. Okay, so these many steps are contributed by the composite numbers, and all these steps are contributed by the prime numbers. So now you'll think, if you have to take the sum of this and find the complexity, that sounds, that sounds very tedious, because this is a very weird sum, right? So yes, it is actually a very difficult sum. You have to use a lot of mathematics. So let's just see how we can approximate this value. So this value right here, let's just ignore for now. Okay, the part of the time complexity contributed by the composite numbers, let's just ignore for now. This right here is the part of the complexity is contributed by the prime numbers. Okay, so this right here, for this complexity right here, n by 2, n by 3, plus so on till n by p. Okay, this we have to find an approximation to. So if you find approximation to, we definitely know that this particular value, that is this particular sum, is less than once again, I actually will just remove this n factor from it. Sorry. So there's this n factor common to all of these, right? So I'm just going to take it commonly. Okay, and I'm just going to write it like 1 by 2 plus 1 by 3 plus 1 by 5 plus so on 1 by p. So let's just say we have to take the sum of this right now, this particular thing, to understand what the total complexity will be. So to take a sum of this, it's difficult. Like it's the sum of the reciprocals of all the primes, which seems impossible. Like it seems like a very big mathematical problem. So we will try to take another sum instead. Let's say let's try to take the sum of 1, 1 by 2, 1 by 3, plus 1 by 4, plus 1 by 5, and so on till 1 by p. See, we know that this sequence is definitely less. This sum of this sequence definitely less than sum of this sequence, because this only contains the prime numbers. This contains prime and composite and all other kind of numbers, like till p. It contains 1 by 2, 1 by 3, 1 by 4, 1 by 5, 1 by 6. Okay, and so on. Has been 1 by 6, 1 by 7, 1 by 8, 1 by 9, 1 by 10, like all numbers. So this contains prime numbers and composite numbers. Just I'm trying to take a reciprocal of all numbers and a sum. So we know this is definitely less than this value. So this you can actually approximate it around to being like an integral. Like you can this once again, I'll just write it in summation notation. This is basically just sum I is equal to 1 to p 1 by I. That's all I mean. You understand? So this is just the sum of the reciprocal values of 1 to p. And this you can like approximately write it as an integral from 1 to p 1 by n. Oh, sorry, not 1 by n, 1 by sorry. So 1 by x dx you can write, and this approximately, or not approximately, this is equal to log of x p, and 1 equal to log p. So understand. So this comes around to log p, and p, as we know, is the largest prime number. Okay, I rubbed that, but basically p is the largest prime number less than n. So we can approximately say this would be approximately equal to log of n. Okay, because like p won't be very much smaller than n. It is the closest largest prime to n, so it won't be very much smaller than n. So we can say this is log of n. So see, log of, so this sum we can say is less than, definitely less than log of n. Okay, so this sum right here is definitely, this sum right here is definitely less than log of n. And there was a factor of n here. See, this n factor is here, right? So I just put that n factor also. So if you multiply n on both sides, okay, this thing's complexity is definitely less than n log n. Okay, this thing's complexity is definitely less than n log n. You understand? like that we were able to derive. So yeah, so this is just, I was just showing you a way to approximate how much the complexity of an algorithm can be. This might seem a little bit complex to you right now, not gonna lie, but don't worry about it. It's not like you don't need to. It's just for just a fun analysis of an algorithm. You guys, if you don't understand it now, I think you can just go back and watch this part again. So basically, we just approximated this algorithm to be around n log n. And also in the beginning, we had omitted a factor of n minus k. So this k is very negligible because the number of primes is, under when n becomes larger and larger, the number of primes under n also becomes significantly small, like compared to n. So this you can approximate it as n, and you can call this as order n. So you can add this above n plus this n log n. Okay, and you can say that our C of Erasmus complexity, time complexity, definitely be less than this. Okay, now this is just a way I showed you how you can approximate. In like this much complexity is definitely not there for just doing a regular questions. Just I want to give you guys a nice idea on how this thing is done. That's all. So that's that. And so this is just an approximation. This again, this you can further, approximate it like to around order of, around order of n log n. You can further approximate it because log n is a big value. So in comparison to log n, so like see, this is n plus n log n, right? N into log n. So this can be written as n into 1 plus log of n. So this 1 is a very small value, so you can just omit it, and you can just remove this value because it's a very insignificant value. So n log n, you can approximate that complexity n log n. Now, so this is just a way how I showed you how even if you can't exactly say what the complexity of a algorithm is, you will be able to approximate it somehow. Okay. Now the real complexity of this algorithm is what? It's n square log of n. This is a very huge proof. It uses a lot of big concepts, and like if you all want, I'll put in the chat box. If you all want, you can check it out later on. But like it's a very big proof. So that's how the real complexity is got. But what I showed you is just how to approximate, just according to your need, how you can approximate the complexity. So don't worry about it. Even this seems, I understand this might look a little bit complicated. This might look a little bit big. This just, just we are learning. So I just showed this, that's all. In a real, as we do more and more real problems, you will get an idea of how to actually see the complexities of a problem even before, like when you think of a solution in your head, you'll be able to say, okay, this much complexity is coming, and you'll be able to decide whether you want to discard your solution or you want to keep your solution based on that. So in the upcoming weeks, you'll definitely get a better idea of this. So I think I actually wanted to discuss something else, but I think we're running out of time. But yeah, so we are done with complexities, and we are done with the C of Erasmus thing. So for today, before like now we are finished with the speaking, like the studying part of our uh, of our session. So I just wanted to give you guys, a quick like introduction to the, not introduction, quick like feel for competitive programming as a hobby instead of, as something, as a tool for your interviews and stuff. Instead, I just want to give you guys an idea of what really competitive programming is. So that's why I showed you all the C of Erasmus, just to, get an idea introduced into your head. Okay, so you guys can try plenty of problems. You guys can try plenty of stuff. I would definitely recommend, like if you're going to do problems and stuff, I definitely recommend code forces. Like I did most of my most of my studying for competitive programming from code forces. like I've written over 70 contests in code forces, and I should say like their problems are very spectacular. It's very beautiful to solve. Y'all should try it out as a hobby. You should keep competitive programming as a hobby. Because it it is a really good tool to improve your problem solving skill. And as we know, problem solving skill is a very useful thing to have in any field of computer science. Like uh, you go to machine learning and artificial intelligence, or you go to what else is there? You go to cryptography, or you go to like web development or app development. Everywhere you need a basic problem solving skill and also a very nice debugging skill. And all of these things are provided to you by competitive programming. And um, you should always see it as a hobby, seeing it as a hobby and continuously doing it on a day-to-day basis. See the fun of it and do it. And I think best place for that is Code Forces. Code Forces is basically the biggest platform for competitive programming, biggest discussion platform also for competitive programming. So like you guys can just later on try out the contest. There is one today, I guess, in 1 hour. So you don't need, I mean, if you want, you can do this. You don't need to do this. We are also preparing a contest for you. Actually, we are going to be doing that. But you guys can definitely try this contest. It's like within what? It's after 24. It's about day, day after tomorrow. So you guys can definitely try this contest. Normal code force contests are only like 2 hours, and in a week there'll be like what, 2 contests max. So you all will be able to just give 2 to 4 hours a week and do a bunch of very nice questions. Um, so yeah, so you should definitely have fun with competitive programming. Don't see it as as something very tedious or something difficult to do. Uh, Instead, you should keep it as a hobby, keep it as a fun activity. And also, like why I recommend Code Forces specifically is because, like, I understand that generally many people feel that Code Forces might be a difficult platform. Okay, but the thing is this: it's not difficult. It's that in on Code Forces, when you do a problem, they don't expect us to only code. So the thing is like this, I'll tell you, as computer science engineers, when we get a problem, we immediately like to jump on, we have the urge to suddenly start coding, like immediately start coding. And that is not exactly how competitive programming is. So in competitive programming, you have to, it's competitive programming. It's not competitive coding, you understand? So what you have to do is you have to, uh, if you get a question, like if you all are trying this contest, I'd urge you to definitely try this contest. And what you can do is you can take a nice question, okay, from this contest, and then have a few pieces of paper with you, okay, and a pen, and you'll find a very, you can play around with your problems. You play around with the problem statement. You see what all observations you can make, what all patterns you can develop from the problem. Try different test cases, try to find patterns and write it on paper and create a solution, and only then go forward to uh, actually coding it. Okay, like so first, create an algorithm, create a solution by observing different patterns and observing different things in the question, and then you go forward and code it. And that's how you do a proper competitive programming question. And that sort of a mentality is what helps you um, improve your problem solving skill, and that sort of a mentality is definitely promoted by Code Forces. uh, so yeah, so that is what I had to tell about Code Forces. And also another thing is like, I understand that in this platform, specific platform, like div 2, so this is a div 2, rated for div 2. Div 2s are written by like 26,000 people. Div 3s are written, no, I mean like by around 21,000 people. Div 3s are written by around 26,000 people. So there's a lot of people writing it. Okay, and your rank might go low. You might not be able to get a question, but don't worry about it. Like that is not the focus. The focus of competitive programming or doing questions in a contest is not to get highest rank. No, it's to learn. So you don't need to worry about not getting a question or not being able to do a contest properly. You should just sit down and try it, and eventually you will get, you will improve your problem solving skill. You'll see a marked improvement in your performance. Like for me personally, I told you I wrote over 70 contests on Code Forces already. And like the first 5, 6 contests, I wasn't even able to solve the A problem. Like you can check, like this is my username. You can check my profile if you want. I haven't even been able to solve. Wasn't even able to solve the A problem. But eventually, after about 3 to 4 contests, I was able to solve the A problem. Then I was able to solve the A problem faster. Then I was able to, within the span of the contest, I was able to solve the A and B problem. So on and so forth. Like I have definitely seen a marked improvement in my performance in competitive programming, and also a big improvement in like debugging skill and general problem solving skill, even when it comes to other things. Like if I'm doing web development, uh, even there also I see a lot of difference in this. So you guys don't need to worry about the ranks and marks or anything. Just keep trying contests, keep having fun with, competitive programming. See it as a hobby. Don't see it as, a tool that you'll use any day or it will help you out. Just have fun with it and it will really reward you. You understand? Just have fun with it. And like I said, take a piece of pen. Like when you're going to write a contest, take a piece of pen and paper and just read the first question, the easiest one. So sit down, you read, take the open first question, you just read it, you understand it, what they're asking you to do, and just try to try to make observations, try to check the different test cases, and you just try to find patterns in test cases. Eventually, you will be able to create a solution, which then you can further move on to coding it and submitting it. And also I would like to say that like after the contest and all, the Codeforces forums are really amazing. You guys should definitely check it out. If for example there's a contest and the tutorials, okay, the tutorials, like they have the solutions, like after contest the solutions come, and the comments, in the comments and all, like a lot of people give their solutions, and a lot of people of different, different, like, see, this guy is a blue level coder, this guy is um, uh, what, he's a cyan, or he's a specialist and he's an expert. Of course, different people of different level will be speaking. You can ask them doubts, you can interact with them, and you can see their code. After a contest, you can, if you tried a problem for half an hour not getting the solution, you can check out somebody else's solution and you can learn from it, you can study from it. So yeah, so I'd really urge you guys to try Codeforces and to check out this particular contest. You can definitely try it out. As for today, we have actually made a contest for you guys. I think Neeraj, would you please send us the link in the chat box?
Yeah, just a sec. So we have made a contest. It's going to be for 45 minutes and contains 3 problems.
Actually, where's the chat box? I am not able to see it.
Just in I think the top right, like right here again. Just.
No, bro, it's not there. Except chat box,
yeah.
everything else is present.
It's
not visible for us.
Oh, okay, I see. Okay, then I think we'll send the link on the WhatsApp group. There's a WhatsApp group, right, for this particular event. I think we'll send. Then Neeraj, would you send the link? I think we'll just show them how it works.
Yeah, I'll send the link in WhatsApp group, and then if you want, I'll just share my screen and even show you what the contest will be. And it starts at 7:30 for 45 minutes. Okay. And there are 3 questions based on time complexity.
So would you be showing that, or?
I'll just show it and then you can show them how to join it.
Yeah, sure.
So as you can see that if I go here 1 sec, I can't. Can I hide this? Yeah. So when you go to the group, we'll give you the group link to join. in the WhatsApp group. When you go to your group, this will be the group link, and when you click on it, here will be a contest. As you can see, it starts at 7:30, going to be for 45 minutes. Make sure you guys go and register for the contest before, otherwise you won't be able to join the contest. So make sure you register it, and then I will you guys can start doing the contest. And there are going to be 3 questions in it. And now Sanjay will show you how to actually join the contest if you guys are new to Code Forces.
Uh, Actually, Neeraj, I can't open WhatsApp, so can you just send it here also in the chat box? I can see the chat box, right? I'll open it from there. So I guess
I have sent it in the chat box. That's what it. I'll send it to you as a DM.
Okay, yeah, sure.
This format as shown. I've sent it.
Okay. Or actually, the issue is I can't show my DM, right?
I sent it on Teams if you want. Because
okay, actually, I'll just. What is the name of the session? I'll just open it through, I think, groups. You can go to groups. The MIC. What is the name of session? Can you just tell me the name?
MIC_competitive_programming_practice_session.
Program practice session. Okay. Yes, it's. Okay, I can't find it. I'm not sure. Actually, Neeraj, you do something. Can you just share a screen? You can show it. That's all. I think you can just show it, right?
Okay, I can just show you how to go towards it. Okay, fine. So I don't know what's the issue with the link. Okay.
I'll open the link in the meantime.
As you can see, I've sent it here. So all you have to do is just click on this link, which will be there in your WhatsApp. You'll be then redirected to a group like this. And here will be a button as join. So all you have to do is join. And once you join, you can see this contest. And here will be your, just a second. Yeah. So here will be a register button. You can click register and then you have to wait until this starts. So once I register here, all I have to do is click on this register button. You're registered for the contest. And once you're registered, as you can see, there's time. So before you start 27 minutes. So until 7:30 you have to wait. And after 7:30, if you click on enter, you can then enter your contest. And there are going to be standings and everything, but you guys don't need to bother about your ranking or anything because it's just a practice contest. So try to at least solve all 3 problems. Try to solve it, as it's all of them are based on time complexity. There is no any other logic required in it.
Okay, I think I have.
We
I
should
was able to
click on
get
join, right?
Yeah, join.
Yeah. Once you
click on
get the
join.
group, just join it. And if you guys want me to confirm whether you're there in the group or not, you can just tell me. I'll just confirm, give you a confirmation if you've joined the group or not. If you want to tell that, tell me your code forces ID and then I'll just confirm if you've joined it.
Bro, Krishna Prasad.
Yeah, you're there.
Yeah, bro, thank you.
Yeah, as you can see, just click on join, you'll be invited. And as long as you can see the contest. So Krishna Prasad, you're joined, right? You can see the contest, right?
Yes, bro, I have
First
registered.
week. Okay. So as long as you can see the contest, yes, you're in the group.
Okay, can you confirm my Pabak code? Oh, sorry, sir. Code Forces ID you mean, right?
Yeah, you're there, you're there. I've seen it's there.
Yeah, so is just I've got the link. So yeah, just for those who did not understand, just if you click that link that's shared in the WhatsApp group, you will reach this particular you'll reach this particular place. You can just down here there's join. There's only one option, join as participant. So you can just click on that. Yeah, and I've successfully joined. And then you can just register for this by clicking here, and by clicking as individual participant is checked. So just register here. Yeah, so like the registration has been complete. For those who do not understand, yeah, this is the only step involved.
Also, do make sure you guys join the group. Not only just click on register and leave, below the option join if you really want to check your standings or anything. But it would be better if you join the group.
Yes, so I guess if you have joined, I think you can, to confirm, I think you can see this leave button, right? Yeah. So this is just the confirmation for whether you've joined or not. Yeah, so I think we've covered everything for today's session, right? That's it for today's session, I guess. If you all have any doubts, you can say now, I guess. And yeah, if you all have any doubts, you can say now. Like you can unmute yourself and ask now, or I guess you, we have a WhatsApp platform, so right? You could ask there also if you want to. Okay, if nobody has any doubts, like we can end it here, right? If that's the case. Neeraj, you should say.
Yes.
Yeah, we
If
can end it here.
other doubts, we